All right, welcome everybody. Let's finish up chapter 2. Within this, we'll talk about scatter plots, correlation, and linear regression. So what I'd like you to do is take a second, pause the video, copy the notes for the lesson. So here we have correlation. A correlation exists between two variables when the values of one variable is somehow associated with the values of the other variable. We'll go through some example very soon. A linear correlation or a linear regression exists between two variables when there is a correlation and the plotted points of paired data result in a pattern that can be approximated by a straight line. We'll get to that very soon. And for a scatter plot are just your x and y values. And remember that this is your x-axis over here and this is your y-axis over here. Okay, so let's go through some example. Here, just really quickly, caution. The presence of correlation between two variables is not evidence that one of the variable causes the other. And I'll explain what this means very soon. But let's take an example of, let's say if we have somebody, right? And whatever their waist circumference is, notice how if we had one person who weighed, let's say 100 kilograms, which is, what is that? That's like 120 or 30 pounds. Notice that their arm circumference over here, notice how there is some sort of correlation between waist circumference and arm circumference. And here, this is what it's stating here, that pattern suggests that there is a correlation or relationship between the waist circumference and arm circumference. Noticing how we have some sort of positive correlation where the x and y data values create some sort of linear pattern. All right, let's continue on and we'll do more examples of this. Here, in a lot of other studies shown, if we have somebody, in the other previous example, we did weight and arm circumference. But what if we tried pulse rate? Here, based on beats per minute, what I'd like you to do is have this in your notes. Notice that the weight of an individual seems to have no correlation with their pulse rate. So when you think of pulse rate for a human being, weight could be a factor, but there could be other factors such as stress that may cause, or maybe even genetics, where someone could have a higher pulse rate, but maybe they don't weigh as much. So here, within this data values in scatter plot, notice how the data values are scattered and there is no line that best fits like in the previous example. Okay, and this is the idea of the line that best fits is a linear correlation coefficient. So please have this in your notes, but it's denoted by R and it measures the strength of the linear regression associated between the two variables. So back in Algebra 1, I'm pretty sure a lot of you may have calculated R. And how did you calculate R? You used a calculator. Okay, I know for a fact you used a calculator to calculate how strong a linear regression could be. And how do you actually calculate the value, or how does your calculator calculate R? It is this monster of a formula where R is equal to these within this equation, right? So this, I will not cover the formula for R. This is extra credit, and I will try and I'm gonna make a separate video for this, but it's nice to have in your notes. How do you actually calculate R, and what do these symbols denote? This sigma notation will be very important, and this little n notation will also be very important, and we'll talk about that in a separate video. Okay, so please also have this in your notes. So R is usually found on the calculator, but we could also do it by hand, and that's what I was talking about before. And what does it really mean, the linear correlation coefficient? So the idea of slopes are going to play into field. So our linear correlation coefficient is always between -1 and 1. So what I want you guys to do is just be patient while I kind of go through this with the next section. So please have this in your notes, right? And let's take a look at this. If we looked at these data values, right? So if we had the time of a movie, how long a movie was, and its star ratings, notice how we have one data value here, one data value here, one data value here, one data value here. The idea with linear correlation is, can we create a straight line? What is the line that best fits these data values? So notice that if we have data values such as this, notice how the values aren't very close to each other within this line, but we do have some sort of positive, notice that this will be some sort of positive correlation because the slope of the line from left to right, it's increasing. So we have some sort of positive correlation. Here, if the data values show this sort of trend, we're going to have a negative correlation, and the value will be somewhere between -1 and 0. Remember the idea, your value of R will always be between -1 and 1. Okay? So you could get other examples where if we have some sort of correlation where the data values, where the line that best fits doesn't have a positive or negative slope, notice that what is between -1 and 1, you could also have some sort of R value that's equal to 0, and this states that there's no real difference between the longer and shorter movies within this rating. Okay, and just to recap over here, that when we have the value of R, it's between 1 and -1. You have positive and negative correlations, and yeah. So how do we actually, what determines the value? So the next question we have over here is, what determines the value of R? It's like, let's take a look over here in the previous example that we had, in the first example. Notice how if I were to draw this line that best fits, right? Notice how the data values are very close to this line, right? The data values are very close to this line, so I can guess that my R value is very close to 1. Okay? Because the data values are very tight. And let me go through this example here. That if I had, let's take a look at these 3 slopes over here. Notice how if I had these 3 examples, notice how within this line, you see how the data values are very close, or they're very tight. This is very close to 1, and notice how the linear regression is at 0.81. Here, it's not as tight, and here it's much more spread out, so our R value may be closer to something like 0.32, but they're all positive correlations. Okay, so how does the linear correlation figure this out? It compares 2 things: the scatter along the y-axis, and the scatter along the data the scatter along the data of the fitted line. So the way R is calculated, it's how close the data values are to the line that best fits, whether it's a positive or negative slope. Okay, and yeah, that I guess is it. What did I write over here? This is not too important. And here, notice within this example, there is 0 correlation. Okay, to get a better feel for linear regression, there is a nice little quiz I have for you for quiz number 1. It goes through basically chapters 1 and 2, and in the last section, you will go through an example with linear correlation. So what I'd like you to do is kind of go through the quiz, and for this final part, we will review this together when we meet up in class. Okay, but what I want you to do is to understand the final section of chapter 2. Going through this example may help you understand the notes that we had over here. Okay, I will see you in class.